Bridging simulation and reality. Part 3 leaves the benchmark and enters the physical world. We now examine the hardware, calibration, localization, and deployment work needed to bridge simulation and reality. Parts 1 and 2 built a theoretically solid stack, foundation models for reasoning, cooperative spatio-temporal fusion for perception, risk map for interpretable planning. But there is a well-known problem in robotics called the sim-to-real gap. Systems that work in simulation often fail when deployed on real hardware. The reasons are concrete. Sensors have noise characteristics that simulation doesn't perfectly model, and the physical world has edge cases that no dataset designer anticipated. This part covers how to build, calibrate, and deploy a real V2X system, from the hardware to the algorithms running real-time on a moving vehicle. The testbed for this work is a real intersection on the UCLA campus. It is an active public intersection with real vehicles and pedestrians operating every day. Running multiple agents with multiple sensor types introduces an immediate synchronization problem. A vehicle traveling at 60 kilometers per hour moves 0.83 meters per second. A 50 millisecond timing offset displaces the reported object position by more than 40 centimeters. The solution is hardware-level synchronization. GPS provides a shared global time reference visible to all agents simultaneously. Every sensor lives in its own coordinate frame. The camera has an intrinsic model that maps 3D world points to 2D image pixels, including lens distortion. Extrinsic calibration establishes the rigid body transforms between all of these. If any of these transforms are wrong, point clouds from different sources fuse incorrectly, producing ghost objects that appear to exist but don't, or missing real objects entirely. The next challenge is ensuring the data you collect is diverse and representative enough for training. Data collection at the UCLA Smart Intersection follows a structured protocol. Capturing the full range of spatial overlap patterns, data was collected at multiple times of day. This structured approach produced the V2X-real dataset and V2XPNP-SECU described in Part 2. Cooperative perception requires that all agents share a common world model, and that means every agent needs to know precisely where it is in the world. Consider the scenario. An infrastructure node observes an object in its field of view, and a vehicle observes the same object from a different angle. To fuse these two observations, both agents must know their position and orientation. If their localization is off, the fused result is a corrupt representation, worse than either individual observation alone. Precise localization is not optional for cooperative systems, it is load-bearing. The solution is a multi-rate aerostate Kalman filter that fuses 3 sensor modalities with very different characteristics. GNSS provides absolute position. It grounds the vehicle in the global coordinate frame, but operates at only 5 Hz and degrades significantly near tall buildings. The IMU and wheel speed sensors provide high-frequency velocity and attitude updates, but they accumulate drift. LiDAR map matching compares the current point cloud scan against a pre-built HD map to correct pose, but computationally expensive. The Kalman filter integrates all 3 streams and produces a continuous smooth pose estimate. The output is lane-level accuracy. With precise localization established for every agent, the core algorithmic question can be addressed. How do we actually fuse observations from different agents in real time? CooperFuse is the first real-time cooperative late fusion system. Late fusion means each agent runs detection locally, transmits its detected bounding boxes, and the receiver fuses the results. It is lightweight. The challenge in late fusion is deciding which bounding box to keep. Traditional NMS simply keeps the box with the highest detection confidence score, but confidence says nothing about the physical properties of the detection. CooperFuse fuses using the temporal features of each bounding box. Temporal feature fusion captures that geometric quality. Light fusion is bandwidth efficient, but it discards the richness of intermediate feature representations. Sharing features before the final detection step can unlock significantly higher accuracy. V2X Riello is the first online intermediate fusion system. The system operates at 0.5 megabytes per message, a 32 times compression of the uncompressed BEV feature representation. This size fits within bandwidth budgets. BEV features encode both static environment structure and dynamic object features in a single spatial representation, making them an efficient intermediate for multi-agent fusion. The next engineering challenge is deployment. How do you develop and validate these algorithms without requiring a full hardware cycle for every change? The answer is a principled bridge between simulation and the real vehicle stack. Developing and testing these systems requires the ability to run the same code in simulation as on real hardware. OpenCDA-ROS bridges simulation and reality, implements the full V2X communication stack so that code written for the Carla simulator can run directly on real vehicles with no algorithmic changes. CDA SimBoost closes the loop between real-world data and simulation-based training. The pipeline, import real-world sensor data, reconstruct the physical environment, use the digital twin to generate challenging scenario variants, train and benchmark cooperative perception and planning systems. Why generate scenarios? Because real data is overwhelmingly nominal. Sensor failures, rare pedestrian behaviors, occluded intersections in heavy rain. These events are statistically rare, but disproportionately important for safety. The digital twin is the mechanism for controlled exposure to edge cases at the scale needed for robust training. The digital twin is not just a visual replica, it is a physically consistent simulation environment built from real sensor measurements, preserving the spatial geometry, sensor placement, and traffic patterns of the actual intersection. The environment supports swapping sensor configurations, adding virtual agents with programmable behaviors, and injecting sensor degradation models. This makes it possible to evaluate how a cooperative perception system responds to partial sensor failure. A digital twin this expressive needs a systematic data generation interface. OpenCDA InfraX is the data generation platform built on top of the digital twin infrastructure. It provides a unified interface for generating multimodal sensor data across flexible configurations. The platform is designed to feed downstream model training directly. Structured annotations, calibrated sensor data, and ground truth labels are produced in a format compatible with standard training pipelines. This part built the entire infrastructure layer for real-world V2X deployment.